In this example, we have two capacitors in a given circuit, and we have 4 resistors and 1 battery. We have also a switch, and this means that, well, sometimes we close the switch and sometimes we will open it. So we named all the necessary points on this circuit. Sometimes we need to label the potential for some points, and we will be able to apply the loop rule of the Kirchhoff's. But you notice here the point A is grounded. That means whenever you have a grounded this shape, parallel 3 lines, that means the potential at that point will be taken as 0. Okay, so the ground potential is always 0. So this is the rule, and we have 50 volts battery. So the question is, first of all, what is the main current through the battery when you close the switch at time t is equal to 0? So initially, for momentarily, when you close the switch, the current will be provided by 50 ohms of battery, and this main current, of course, after you close the switch, will change because of this capacitor. Whenever there is a capacitor in a circuit and current flowing through it, the current will change over time. So initially, one thing we know about the capacitor circuits, the capacitors will act as a short circuit. That means, for example, when you close the switch, the potential of point D and F will be the same. It is as if there is only one wire which has no any resistance, nothing. So the capacitor will act like a short circuit. And the same thing is true for this capacitor also. The potential of point E and G will be the same, as if we have only one wire in here connecting these 2 points, and current is flowing through these points without any resistance. So you will then see that there are no capacitors at time t is equal to 0, and these are just wires. And in that case, these 3 resistors will be parallelly connected between points D and G. So since these points are the same potential VD and VF, then as if we have 3 parallelly connected resistors. So we can, first thing we can find the equivalent resistance between point D and G, and then these equivalent parallel resistors are connected to this 10 ohms resistor in serial, and you can calculate the equivalent resistance of the circuit, and then you find the current provided by this 50 volts battery by using the Ohm's law. But before we start attacking this first problem, A, then what is the problem after this? You will find the current this time for a long time. Okay, when you close the switch S and wait for a long time, that means technically time is running to infinity. Or if you wait for long enough time, in that case, what will be the current through the main branch of the circuit? In that case, what happens, you think, when you close the switch, when initially there is short circuits between point D and F and E and G, because the capacitor will act like a short circuit, but once these currents flowing through this capacitor, initially the capacitor will get charged, right? When the current flowing through these capacitors, the current will accumulate charges on the plates of the capacitor, but by accumulating the charges on the plates, there will be potential difference between points and D growing. That means the current will, since this potential difference will increase, the currents will decrease, right? After waiting for long enough time, these capacitors will act like open circuits, right? There will be no current flowing through these capacitors when the capacitors are fully charged, right? And that means these branches between points D and F and between points E and F, E and G, the branches will act like an open circuit. So there are no current flowing through these circuits. In that case, all the currents coming through to point D will flow through 15 ohms and since there is no way to go from here to here, the same current will flow through the 12 ohms resistor, and it will go again through the second 15 ohms resistor. It will go continue like this. So it is as if these three resistors will connected serially to each other, right? If you wait for long enough time, then in that case, these three resistors act like a serially connected resistances. Then the rest is easy. Just find the equivalent resistance of the circuit and find the main current through the main branch by using Ohm's law again. Well, the next question is, if you again wait for long enough time, what will be the charges accumulated on each of these capacitors? One is 10 microfarads, the other is 5 microfarads. So you'll able to find, after waiting for long enough time, the charge accumulated on these capacitors, first by finding the potential difference between point and F, right? And we can do that when you know what the current is, main current is flowing through these resistors. It is easy. Whatever the potential of the point D is, the potential drop from this point to F will be just the main current I times 15 ohm plus again the same main current I times 12 ohms, because the potential drop can be expressed by the current multiplied by the resistors. So it's easy. Alright, let's start first the first question. What is the current through the main branch when you close the switch initially at time t is equal to 0, right? So at time t is equal to 0, as I said before, these potentials of point D and F and the potential of point E and G are the same, because these capacitors will act like a short circuit. The current, exactly whatever the current comes to point D, flows without any resistance to point F. And again, it's the same. Just imagine that there are only cables between point E and G and D and F, and then the currents, the resistors between point D and G will be parallel to each other. So next thing is just calculate the equivalent resistance of these three resistors which are parallelly connected, right? And this is easy. Just inverse resistance of equivalent resistance. Just inverse inverse of the 15 ohms and inverse of 12 ohms and inverse of again 15 ohms, all added to each other. You find the equivalent resistance in that case as 4.62 ohms. It's just an algebra. You can do this without any problem. So the result of these three resistors are parallelly connected, and they are equal to 4.62 ohms, but this resistor is connected to 10 ohms serially. That means the equivalent resistance of the circuit is 10 plus 4.62, and once you know this total equivalent resistance of the circuit, by using the Ohm's law, you can find the current initially at time t is equal to 0 as 50 volts divided by this 10 plus 4.62, and this is 3.42 amperes for the main branch current at time t is equal to 0, right? But the current will immediately drop to this from this value slowly to a 0 value after some time. Well, not 0 value, sorry, because the main branch current will always be going, but it will change slowly when the capacitors are getting charged. So this is the answer for the first part. And the second part, when time goes to infinity, if you wait for long enough time, then in that case these currents through point D and F and point E and G acts like an open circuit, because there will be no currents flowing through, because the capacitors are fully charged. In that case, the currents will go from C to D, from D to E, E to F and G, and it will be the same current flowing through the main branch, and all resistors, all three resistors will act now like a serially connected resistors. And then the next thing is to just calculate this equivalent resistance of the circuit, because all resistors are serially connected, And first of all, the equivalent resistance of these three resistors are 15 plus 12, which is 42 ohms, right? But you will add this total resistance to the 10 ohms also, because this is also connected serially, and then apply the Ohm's law, right? So the Ohm's law for if you wait for long enough time is 12 volts divided by 10 plus 42, and you will find the current in that case drop to value 0.962 amperes. Okay, it's 0.962 amperes as the current, only current flowing through the main branch of the circuit if you wait for long enough time. So next is we will calculate what the charge on 10 microfarad capacitor if you wait for long enough time. So we know that the Q and C and the potential difference across the capacitor by using this Q is equal to C times V formula. And so we know what the C is, it is given in the problem initially, but we don't know what the potential difference between D and F if you wait for long enough time. Well, if you wait for long enough time, we know what the current is flowing through these points, and we can calculate this drop from D to F by just following the current through 15 ohms and 12 ohms resistors, and by crossing 15 ohms the current will drop I, which is 0.962 amperes times 15, and it will continue to drop again the same current 0.962 times 12 ohms. So you can now whatever the value of the potential at point D will be dropped by this amount, right? So we can calculate this drop in the potential as 15 plus 12 ohms times the current flowing through them. So you multiply this value by the capacitance of the 10 microfarad capacitor, so you can find the charge then. What the charge is, just a simple multiplication. The charge is 360 microcoulombs. So you can do the same for the second capacitance, to find the charge of the second capacitance. Then in that case, the potential drop from point E to G is just the current value, which is 0.962 times the total of these two resistors, because they are serially connected now. And let's do that. 5 microfarads will be multiplied by 12 ohms plus 15 ohms times this value of the current. And it's easy. When you do the multiplication, you just find 130 microfarad as the this will be the coulombs, microcoulombs. There is a mistake in here. I have to get rid of this. Okay, this will be coulomb, microcoulomb, right? So this will be the charge of 5 microfarad capacitors. Alright, so this will end the solution.